Hello, so we'll start with the code. Okay, I'll explain the code. Then you all can basically use the code, train the model, and yeah, upload it on the drive. Okay, because we already missed a lot of lectures. Okay, so what I'll do is I'll explain this code. You all then run it. I'll try uploading the data set as well. Okay, then once that is done, we are done with CNN as well. All right. So let's start. So the first part, okay, this is basically importing the libraries. Okay, uh, so I'll explain these libraries as we go. Most of the libraries like TensorFlow I've already explained, right? Keras. Then okay, this is a new one. Okay, this is a new module. So we start with like basically pre-processing the data. Okay, that we are giving it as input. Okay, so what we'll do is we'll pre-process the images. Now there are multiple ways to pre-process an image. Okay, you can either zoom it in or rotate it or horizontal. Like you can flip it. You can rescale it. So what's the purpose of doing this? Last time we discussed pre-processing basically CSV files, missing values. In this case we have images. So what's the point of basically pre-processing? So this is in order to basically avoid the situation of overfitting. So I've already explained what is overfitting. It's when the model is too lenient or it gets fitted to the data that it is trained on. So if tomorrow we give it some new data, some new input that is not closely related to the input data set, then it might not be able to basically perform the accurate predictions. So in order to handle that, we need to basically pre-process the images. Now okay, so for that we are going to use the image data gen class. Okay, generator. So what this does is it basically has multiple methods within it that when applied on an image basically performs these operations. So now where do you get this code? Okay, so what you do is you go to TensorFlow Keras. Again, that there is data pre-processing. Okay, let it load. So over there you will find data pre-processing module within which you will have image. Okay, there are multiple types of pre-processing. One is text processing, one is time series, and one is image. So for now we will be using the image. Okay, let it load. So for that we'll be using image pre-processing. Okay, so you can read, you can check out like what each of this does. Okay, in the documentation. Shear means basically rotations. Okay, zoom is zooming in. Rescale is basically rescaling the image. Horizontal, like this is just okay. You can understand from the names also. So what we do is first we create an instance of this class with the methods we want. After this, what we do is we use this class. Okay, and we use a method flow from directory. Okay, the first parameter we pass is the directory for or the location of the data set. Okay, so first is that. Then after that we have target. Okay, target size is basically the dimensions, like what are the metrics that we are taking it as input, okay, in order for the model to train. And also while giving an input it should be of the same target size. All right, then next is batch size. So the this transformation will be applied in a batch of 32, so 32 images will be taken, and yeah, we'll be applying the transformations. And also we have class mode, that is binary, since we are doing for a dog and a cat. Okay, so in this particular model we are training for a model to identify whether there is a dog or a cat in the image. Okay, so since there are just two, we are going to use binary class mode. Okay, so this basically helps the model to understand the types of, like how what kind of an output we are expecting. Okay, and the model will train accordingly. Now apart from that we have pre-processing. Okay, so after that, once we do it for the training set, we will do it for the test set as well. Okay, but now remember, for test set, when we're doing it, when you're applying the transformation, we'll only rescale it. Okay, we won't do zoom in. This we did so that the model is trained properly. It doesn't get fitted to the data. The test set is meant for evaluation. So whatever image we give, it should evaluate it properly. Okay, then again, when you're passing it, you pass it the same way you passed it. In the case of training set. So you do it, pass it in the same way. So once this test set is also ready, then we move on to building the neural architecture. okay, for CNN. Now coming to the architecture, so yesterday, uh, or before this the lecture before this, we explained the different kinds of layers in the CNN. Okay, so let's start. So starting with the first line of code, we first basically create an instance of the sequential class. Now, if you remember from the ANN architecture, we also imported sequential class. So sequential class basically, gives you a blueprint, okay, to which you can add multiple layers, different kinds of layers. All right, so this is the same as the ANN. Now coming to the next step. So in the ANN, the next step was basically adding the hidden layers. Here it is not that we are adding the convolution layer. So if you see, the layer is conv 2D, okay, since the 2D image. So here there are certain parameters that we give it as an input. Okay, so the first one is filter. Okay, apart from that we have kernel size. Now activation, this you all know. Okay, and then we have input. So I'll explain you all this filter, kernel, and input size. Okay, so here the filter is basically the number of basically feature detector we use. Okay, so this is basically number of feature detectors. So if you all remember, feature detector is applied on the original image in order to get the convol layer. Okay, or to get the feature map. Right. So here if you'll see from here, right, uh, this is the original image. So we apply a feature detector to get this one feature map. Okay, so this the feature detector. Okay, so here filters represent the number of feature detectors. So we'll be using 32 feature detectors, and we'll be getting 32 basically feature maps. After that we have kernel size. So that basically represents the size of the feature detector. Okay, the feature detector is also sometimes called kernel. Okay, and so here it is 3, so it is a 3 by 3 matrix. Okay, so this is a feature detector and the size is 3, right? So it's 3 by 3. Okay, so we are using here 3 by 3 feature detectors. So the activation is rectified linear unit again, if you all remember. So if you all remember, so here see we are performing rectified linear. We're basically applying the function of rectified linear unit to remove the leniency. Okay, so here we specified it and input shape. So this is basically the input shape of the image. So if you remember during the you know basically transforming the training data set, we gave it a target size for 64 by 64. That means the image will be converted into a 64 by 64 format. And here, this 3 represents the color channel. So if you all remember, colored images have 3 channels, red, green, and blue. So basically, it means, yeah, it represents the number of color channels. Here it's 3. If it was a black and white, it will be 1. Okay. Now, after that, okay, so once we apply this conv 2D, what we do is pooling. So if you see here, the layer we applied is max pool 2D. Okay, with a pool size of 2. So if we go back to our PPT and we go over here. So if you remember, here it is. Okay, if you see this is the size of the pooling. Okay, so it's 2 by 2. So that's the pooling size in the pooling layer. Okay, okay. And strides is 2. So what is stride mean is, see, it started here. The next one was over here. Okay, it was the starting position was here. The next one was here. So it shifted by 2 strides. Okay, so stride is basically the number of cells it shifts after a particular max pooling like is applied. So once this is applied, it will shift 2 units, okay, to the right. Okay, and after that, when it goes to the next one, it is going to be 2 units here below. Okay, so if I show you, yes, it shifted. Okay, it came here, and after that, it went 2 units below. So it started here, now it's 2 units below. So that basically means strides. Okay, say suppose it was 3, then first it will be here. Okay, or even if we take the target size, not target, if we take the pool size to be 2 and the stride to be 3, what it will do is it started here. Okay, it doesn't make sense. So we take it 3, the target, not pool size as 3 and also the stride to be 3. So we started here, the next one will be here, this one. Okay, and the next one will be here down. Okay, and suppose say you reach, okay, to the end and there is no 2, so we just ignore this, we take this 2. All right, so that's how we do pooling, and that was the explanation for the input parameters in pooling. After that, again we apply another layer for convolution and another max pooling layer. just like we did in case of ANN. We applied two hidden layer, right? So here we are basically repeating this. Okay, we are repeating this again just for the machine to understand it more better. And after that, we have flattening. Now flatten, there is no input parameters given. It basically will flatten the 2D matrix into a 1D matrix. And after that, we are passing it to the full connection. Okay, that basically means as an input, this layer will be passed as an input to the ANN. Okay, so it will act as the input layer for the ANN. So if you see, we add a dense layer here. Okay, so now dense layer is the hidden layer in ANN. Okay, so here we have around 128 neurons with an activation function of rectified linear unit. Okay, so the input layer was initialized here. It was passed to the hidden layer of the ANN. After that, we have the output layer. Now, output layer is sigmoid. Okay, now if you remember the graph of sigmoid, it was like a snake shaped graph. Okay, or just a snake shape. Here there's just one neuron in the output layer, basically to tell it's either a dog or a cat. Okay, and sigmoid function will help us basically get the output. So it will return a probability, and then we basically, if you go down, uh, if the probability is greater than 0.5, we say it's a dog, I guess. Others say it's a cat. All right. So after that, we compile it. So this you all remember from the previous ANN model. So compilation is done. And after that, we fit the training data. Okay. Then you all can add, okay, let me add for evaluation, CNN, evaluate the training. Oh, sorry, test it. Okay. So once you all do this, then run the cell, and then there in the if you all go to the data set, right, there is a single prediction by a dog or a cat is there, where the model should basically predict it. Okay, there is a image of a cat and there's an image of a dog. Okay, and if you see here again, we are specifying the target size, so the image should be of this size. So even if the image is of a greater, like a different size, it will be converted into 64 by 64, and we'll be passing it to the model, and the model will predict. So I'll recap it again. So first is basically importing the libraries. So this you all can do even as you all code. Okay. So say suppose say suppose you all are doing pre-processing. So here you all will import TensorFlow, and after that from Keras you all will import image data generator. So for the training data set, we apply multiple transformation so that the model learns over a wide variety of data, and the data is not, and the model doesn't get fitted to that in training data itself. Okay, after that, after we create an instance of this data generator, we use the instance to use a method flow from directory that basically takes the input, converts it into, particular target size that we expect. It does it, you can set the batch value as anything. Here I've taken 32, and then binary, since we know that the output is going to be yes, like a dog or a cat. Okay, so the model will learn. Then after that, we apply the transformation for the test data set as well. But while applying, we only rescale it. We don't apply here range, zoom, range, horizontal flip. This is just for the model to train itself. Okay. So after that, we again transform it into 64 by 64. Then we apply patch as binary. After that, we go to build the architecture of CNN. So we import sequential class that basically allows us to add the layers. After that, we add the first layer, that is a con 2D. Okay, this is the convolution layer. We give 32, we specify the number of feature detectors, that is 32 feature detectors will be used here. We specify the kernel size of the feature detector. Then after that, the rectified linear unit, okay, as the activation to remove any leniency. And then also we specify the input. Okay, that means it should expect an image having a 64 by 64 dimension. Also, it will have three color channels. Okay, so that's RGB, since we are dealing with colored images. Then after that, we'll add the second layer that will basically pool. So in the input parameters are the pool size. Okay, that is the size of the matrix 2 by 2. And after that, stride. So by how many cells is it moving to right and bottom? All right. So basically, pooling is to extract the maximum, the most important of the important features. Then again, we convolute it. Okay, we repeat the steps again. Then again, we max pool it. After that, we flatten it. Okay. So flatten is basically converting the 2D into a 1D array. After that, we pass the flattened as the input. Okay, layer. Then that is passed to the hidden layer of the ANN. So here we have the dense layer, okay, which is a which basically means fully connected layer. Okay, it has 128 neurons, and the activation is rectified linear unit. All right. So after that, we have the output layer, which has a single neuron, and a sigmoid has activation function, which will basically tell us whether it is one or zero. Okay, one means dog and zero means cat. All right. So yeah, once output layer, then you compile it. Okay, here see, we use binary cross entropy again. Okay, uh, to calculate the cost as a cost function since it's binary. We used again the accuracy metric. This is you don't need to take worry much about this. Okay, the important things are here: optimizer and loss. So the loss function is binary, and the optimizer is Adam. So this is Adam basically is a kind of a stochastic gradient descent. So yeah, it helps avoid local minima or handle the cases of local minima. After that, we basically fit the training data or we give the data to the model to train it. Okay. So here it's a okay. You don't need to basically have this uh, line of code because here we give it the validation data. So here it has the training data, okay, and here it has the validation data. So training data it will train it and then it will evaluate itself on the test set, okay, and the epoch here is 25, okay. So if you'll see here there isn't any batch size mentioned because we are not doing it in batch, okay, while training. So yeah, we have an epoch, so it will go through the data 25 times and yeah, that's done. So once we run this code, our model will be trained. Then you all can basically test your model, okay, on this particular image. There are two, dog or cat 1 and dog or cat 2. So basically go and run this code, then you all will get, then basically print your prediction and see if you are getting it. Okay, just try to increase the accuracy. I'll give you all the data set as well. So yeah, so by this we are done with convolution neural network as well. Okay, so congratulations on completing, the image recognition part of deep learning. So after this, we'll be starting with ANN. All right. So yeah.